I've just found my pad of paper as well, actually, so that answers one question for me. So our second presenter in this session is Dr. Mitra, who is Associate Dean for Research and Professor in the College of Information Science and Technology. His current research interests are in the area of artificial intelligence, health informatics, big data analytics, applied machine learning, and visual analytics. In the past, he's contributed in the areas of data interoperation, data cleaning, and digital libraries, especially in tabular data extraction and citation recommendation. I'll just do a quick pause on that. If you combine the skill set that we're talking about in our second presenter with our first speaker's interest in human-computer interaction, this is the perfect marriage of subjects that we need to develop these types of projects. It's great to see the two talks put together like this. Back to Professor Mitra. He received his PhD from Stanford University in 2004, his MSc from the University of Texas in Austin in 1994, and a BTech honors degree from the Indian Institute of Technology at Kharagpur in 1993. At Penn State, where he currently is, he's pursued research on a broad range of topics ranging from data mining on the web and social media, scalable data cleaning, political text mining, chemical formula and name extraction, form documents, and the extraction of data from metadata from figures and tables in digital documents. Again, I could go on a little bit more with more details about our presenter, but I, in fact, would like to stop at this point and welcome him up, and we can get the second presentation on its way. Thank you. Oh, and over here. That was sneaky of you. Right. Okay, so that's okay. So you have 45 minutes. Do you want me to have 5 minutes? Give you some 5 minutes warning near the end? Yeah. Okay. I just want my pad of paper back.
Okay.
Okay. Thank you.
Thanks. Thank you very much for the kind introduction and for the invitation to talk here. Our effort is the effort of a small lab. So it's always daunting to go after the National Digital Library of India. So this is now we are talking about 5 students, sometimes it became 10, sometimes 5 again, and so on. So this is work that we did. And I thought about text mining when Plavan asked me to talk about my work. And I thought I would actually give you a flavor of a few different things that we have done over the years. So I've been at Penn State for about 16 years. And the Chemex Seer is an engine that we created for chemistry. And the predecessor to this was CiteSeer. And CiteSeer is a digital library that computer scientists have been using since, 1998 or so. And this is a digital library, a very focused digital library. So this is a digital library about scholarly work. So essentially papers that have been published. And what initially CiteSeer started from NEC Research Lab in New Jersey. And what they said, well, 1998, this is sort of the advent of the web. The web is still growing up. And what they said as well, a lot of people publish their papers on the web. Like we put our papers on our website. And can we create a totally automated engine which goes in and grabs those papers from the web and indexes things, extracts things from those papers to enable search. So this is how it started. And the issue of rights and access came up. So very soon NEC figured out that, even though these papers are being put by users on their web pages, they have copyright issues and other sorts of issues because of which the company did not want to be hosting that search engine. So somewhere around 2000-ish, it came over to Penn State with Lee Giles, who sort of is a longtime collaborator and my mentor. And he brought that to Penn State, and so then it was hosted at a university. The idea is that Perhaps universities don't have any money, so nobody's going to sue us. But we have not really gotten a good answer to the rights problem. It's still an issue. And I will talk a little bit about that with respect to chemistry, where things are slightly different. So the chemical publisher of note in the US is ACS, the American Chemical Society. And their papers are behind a paywall. And they supposedly, they told us that they employ over 1,000 people to actually maintain that library. And now I don't know what employ means, but they actually have a lot of people's jobs are riding on it. So if we start giving it out for free on the web, then that doesn't work. The CiteSeerX search engine, right now the situation is that it's still there. CiteSeer was the original version, then CiteSeerX is the new version, and we re-architected the engine. It's still there. It still serves about 10 million documents. We get about 1 million hits a day, about 1 million unique IP addresses over a month. So there is some amount of real users coming into our system. And actually at Penn State, after our main website, the CiteSeer website is the second highest visited website, for what it's worth. Now, what we do is we just go. How CiteSeer works is it goes out onto the web and collects these web pages. So how do we know where the papers are? We essentially start from a set of seed URLs. So these are the URLs of universities and research institutes, and we go from there. And we grab PDF documents. And where text mining comes in is that the way we know that this is a scholarly article is if it has references. So that's one of the key signals that this is a scholarly article. So we look at references and we say, aha, this is a scholarly article. Now, we do get emails from people saying, hey, my paper is in your digital library, it should not be there, you should take it down, it's illegal, and then we take it down. So I think the Digital Copyright, DMCA, Digital Millennium Copyright Act in the US says that that's what they have to do. If they tell us we take it down, then there are no lawsuits. So that's how we are doing it. And increasingly, a bunch of publishers are giving people the option to host preprints, which are slightly different, and then you're fine. So, like I said, we were using references to figure out that this is a scholarly article. So we do also get some emails from time to time saying that, thank you very much. Can you please take down this document? I am very honored that CiteSeer thinks that my CV is a scholarly article, but it is not. Well, of course, CVs have your publication records, and CiteSeer does get confused. So this is a totally automated thing where we have the human come in. You can create your account, My CiteSeer, and then you can go in and say this is not a good paper, or take it down, and so on. So of course, with the project of this size, it's not only Lee Giles and myself, there were a whole bunch of others who worked with us. Now, this was around 2005-ish when some of our chemistry friends came to us and said that, hey, you guys have this CiteSeer thing which people are using, why don't we do something for chemistry? So we said, okay, and we got our project funded from the National Science Foundation, and they actually came to us and we said, okay, what do you want to do? And they came and told us, well, we want to search for chemical formulae, chemical names, we want to get data out of tables, we want to get data out of figures, we want to search for experiments. Well, none of these, of course, work on CiteSeer. Because, well, I don't know, computer scientists are not that interested in chemical formulae or maybe the performance results of some algorithm and so on. So, okay, we said, well, we can do these, but we will need to start working from scratch. And so this was the 5-year project. We built a whole bunch of tools and so on. And then one of the issues that we continuously hit at is entity disambiguation. So this is with respect to not only authors, the two author names that are there, are these the same? And that's because the types of issues that come up are that, okay, somebody, because of some family incident, changed their name. Now we have to figure out that these two names are the same. In some cases, the references list names in different formats. So you might say R.J. Smith instead of Ronald John Smith or whatever the name was, and so on. So those are human entities. In the case is that essentially our question is, how do we get the metadata from the data? And from these PDF documents automatically. And so this was what we built. We built primarily two searches. One was the chemical entity search, and tables here, which was grabbing data from tables. Actually, at that point, the chemists were hiring postdoctoral students whose job was to capture data from historical papers manually and enter them in a database. So that was the state of the art then. And then we said, okay, we have to find chemical formula, but we not only do want to find chemical formula, but we also sort of want to find the structure, if we can, from the names of the chemical formula. So the chemical formula names sometimes have sort of structural information, and if you find that, then we can enable some more higher order semantic-based structure search, and so on. But even before we could find chemical formula, the name disambiguation came and hit us because OH could have been Ohio, the state in the US, or the hydroxyl group. And NIH, our tool, went in and said, well, that's nitrogen, iodine, hydrogen, which of course it is not. And that you can know from the context, of course. And so we built these chemical formula extractors. So the basic idea here is that the lesson that we learned is that in order to support a particular domain, we have to go in and figure out what the users in that domain want. And then we have to figure out a way of extracting that information ahead of time and tagging it and storing it, hopefully indexed in a way that we can search and find things fast. So that's what we have done repeatedly again and again with different types of artifacts, a few of which I will talk about. So this was done, in this, getting a 95% accuracy is not that hard, but getting that a 98, 99% accuracy was involved a little bit of working. So for example, gold MasterCard. Now the gold is of course not a chemical formula, and that's easy from the context, but certain other cases it wasn't. So I sort of jumped ahead. So other than formula, we tried to find chemical names, and so we want to find, essentially not only find chemical names, we want to segment them to find meaningful sub-items. So for example, methyl-ethyl alcohol, you have a methyl and an ethyl group, and so on alcohol. And there were some crazily big chemical name, which presumably nobody uses. But in any case, somebody might have put it in there to mess with us. So we had to get this and then automatically segment this up and so on. And then the idea is that we understand these, underlying entities and their relationships, so that there is some, at least in this case, very preliminary and basic knowledge by which it figured out that CH4, when somebody is searching for that, is related to methane, and methane is related to methanol, and maybe it found the CH4 there, and so on and so forth. Going from chemical names and chemical formulae, and we did things where if you don't find an exact match, you actually find, you do similarity search in the chemical structure space, or chemical similarity space. And so this we talked about. So I will skip the machine learning part of how we are doing it. Essentially, it's a classification task, and so I'll skip that. But at that point, this is about 10, 12 years ago, we actually extended the conditional random fields to using hierarchical conditional random fields, because the meaning of a term not only depends upon the immediate context where it is, but there are things that are more likely to appear in different parts of the document. So, for example, if it is in the institution's address or the name in your subtitle just after your name, it's possibly not a chemical formula. It is Ohio, the state. So, depending upon where it appears, it depends on that. And then at the sentence level, certain terms and certain formula, there is a certain probability of it appearing. So we extended the machine learning algorithm conditional random fields to do that. And the segmentation problem we tackled by actually looking at a scheme which looks at the frequency and discrimination of these little pieces, sort of like the morphemes, if you will, and so we took them as sort of the subsequences or substrings, and figure out how how frequent they are, and based on that decide where to cut things. So for example, METHY without the L has possibly not been used that much. But with the L, it has been used. You can find it more. So based on that, we can automatically do the segmentation. And then we did the indexing of the documents based on the formula, and we support sort of like partial formula search. And for that, we need to construct an index. As you know, in a search engine, essentially, Google or whatever search engine you use, the words are indexed, and then based on that, it is searched. So the information that we are extracting from these digital documents were indexed, and then they were searched. All right. So I'll skip there. So this was sort of the big picture, the architecture of that engine. And so on the left, you can see on the web, we have a focus crawler that goes and gets the documents. It converts. There's some pre-processing done. Then the chemical structure and the information extraction was done. Parsers, analyzers, and so on. And you see the document indexing going on there. We not only have the document database, the metadata that has been extracted, the document index, but also the formula index and the name index. So now these are domain-specific entities that are becoming sort of first-class objects that we should be indexing. And in the right bottom, you see the graph mining and feature selection. So there we were going from formula to essentially the chemical structures. And once you get the chemical structures, we were building a database of, oops. All right. Is there a pointer here? No. Yeah, the laser pointer right from here. No, that's enough. Yeah, that's fine. So that structured database there is essentially we were extracting the graph structures and putting it in the structured database. So you can think of it as a structure which has 500 or 1,000 chemical compounds that are in your corpus, and all of that is extracted, and then you can do a structure search there too. Okay, thank you. Yeah. So those are the different parts of the architecture. How much time do you have?
25 minutes.
Oh, that's good. Yeah. So then what we did is we worked on experimental data search. So in this case, what we wanted to do was they wanted to put in data, enter data, and then link the data to okay, maybe my eyesight is okay here. Is it working on the white? Oh yeah, faintly. Yeah, so link the data to the existing literature search. So that's what we were doing. So we were using some OAI metadata format to extract the data. And this is sort of what was eventually what was enabled. So you can search for the name of an author, okay, this person reported some data. And then that data was extracted from that particular paper. And I'm going to talk a little bit later about how we did things, to extract tabular data. And so we extract that data, and then there is a tool called JMOL, which was being used to draw that figure there. And so that was connected, and you can see the data and the metadata. So this was roughly our sort of table metadata extraction. So now I'm going into our work on extracting the tabular data from the PDF documents. And when I say PDF documents, most of this extraction was of sort of digital PDF documents. We did not do scanned images PDF documents. So if you go into chemistry, I don't know, beyond 1970 or whenever we have digital PDF documents from, those are all scanned. And that depends upon OCR, which Professor Das mentioned is still an issue in certain cases. So anyway, we were extracting all of this data automatically from these tables, and then enabled the search engine. So this was just a simple search, not the data extraction yet, but you could search with terms from the table's caption, and it would bring you the page from the page where that table appeared, and it would give you a little bit of a snippet. And if you click on the preview, you could preview that, and there were other tables which matched. In this case, we put a very generic term called flow, and this was on our small scale sample, table data set, which we were playing with, and then it goes in. This is just to show you how things were being showed. So what does this let us do? Essentially, you can search for, who reported data. So what they were doing on things like who reported data on dissolution of certain chemical in soil water. And the system would go and search and bring whatever matched. And then you could give the name of a place, and then or a region, and then it would be, in 1960 this was this, in 1975 it became this. Right now they have their own results, so they wanted to compare with those existing results. So this was one of the applications that they wanted to use this from. Again, this was roughly the system architecture for the table seer system. Now, in this case, in site seer and table seer, and so at the end of the day, we got tired of writing individual search engines. So we made a base structure called Seer Suite, SEERSUITE, and that Seer Suite is sort of the base engine which in any domain will work. It's freely available online. You can download it and you can set up your search engine. And on top of that, we would build these modules. So for example, for table extraction, we did tables here. For figure extraction, we had a figures here. In archaeology, they wanted to search for maps of certain regions, certain times. So we had a maps here. And in that maps here, I think when Professor Das talked about OCR, so in the maps here case, we were trying to OCR all the data from the maps out. And the problem with the maps is that, well, you have a name that's written like this in a curved fashion because the river is flowing like that, and then a road passes through it, and so on and so forth. So OCR from maps was an open problem about 10 years ago, and it was hard, even in English, using standard OCR tools because of that. So we stopped. I mean, we have some of that OCR and the data that comes out from the map extracted. But we also, so we extracted information from tables, we extracted information from figures, we extracted information from algorithms, from CS papers, maps, and so on. And the general strategy for searching at one level is quite sort of standard. What we do is we take the captions of the table or the figure or the algorithm or the map, and then what we try to do is we also look at the references to that entity, document entity, in the rest of the paper. So if you write in your text, in figure 3 we show blah blah blah, we extract that blah blah blah. And now using the caption and the reference to the figure in the document, we sort of now have some content which tells us what that figure was about. And when we also look at that, okay, in figure 5 we show things, we actually look at sentences before it and after it and do a content similarity to figure out, with some penalty for distance, to figure out, just beyond this sentence, how many other sentences are there that are actually describing that figure or that are describing that particular algorithm. And that is also indexed. So when you search for an algorithm, what we give you is, we give you sort of the synopsis, like the synopsis of the table we showed you. So for the algorithm, the synopsis could be 4 or 5 lines where the author is talking about the algorithm. For the map, it could be the same. For the table, it could be the same, and so on. And so that's essentially our general search engine. Now in this case, all of the information, document title, author, page number, which column number, and so on and so forth, and so on, are all being extracted automatically. I mean, the fact that there is a table is extracted by this table boundary detector that you see on the lower bottom side. And one of the heuristics that we use that worked pretty well is that tables usually contain sparse lines. So the number of characters in that line is small because table has more spaces in those lines. And that, using that, whereas if you're writing something, then it's more packed, except for the last line of the paragraph, which we know where the last line of the paragraph is. So the table boundary detector automatically uses information like that and extracts table boundaries. Detecting the table metadata is actually also hard because there is a fantastic paper called The Tabular Survey of Tables by George Nagy, RPI. And the whole paper is written as a table. So the paper is 24 pages, it's a table. And within the table there are, every page has a different type of table. And if you want to look at how hairy the problem of identifying tables is, you can look into that. There are tables which are running multiple pages. And there were tables in this case where cells were sort of fused and then somebody put in a chemical structure. Go figure. And then there were tables where not only there were column headers, but where there were row headers. And in the column headers, there were hierarchical column headers. So you could say input, output, and then input temperature, pressure, whatever, and multiple levels. So when you have the table, we have to first figure out where is the table header and where is the column header, row header, and then where are the data, and then extract all of them out. And we did the best we could, and people were happy. So we tried these different box cutting algorithms which would try to segment the page and then classify each box and so on and so forth. So this shows you some complexity of getting the header. And then there is a footnote there, which is actually a footnote, not data. Not a 1, 2, 3, 4, 5, fifth column, fifth row. And because of that, it actually makes, so we were identifying the columns by space, and that line at the bottom throws us off. So it's, so it's a hard problem. Lots of people worked on it, lots of people are still working on it, and that's where hopefully what Professor Das mentioned in the last talk, that the new generation AI tools will understand a lot of this better and figure out that, okay, that's a footnote and not a row in the table. Anyway, we extract all of that and then create this basically standard XML metadata digital object for a table, which PDF it's coming for, which year it was published, and so on and so forth. So that this is stored first-class digital object now. You can use it for whatever you want. There is also an issue of if you're searching for a table and there is no exact match, then how do you do table search? So we used some variation of table rank algorithm. We played around by trying to see, okay, papers that are more important should get a boost. Papers where there is a exact match should get a boost, and so on, and then mix all of those, do some weighted ranking, and so on. We do a whole bunch with looking at the citation network of the table. So this got messed up, but what we were using was OAI or ORE, which is an object reuse OAI standard. So essentially what it does there is it represents each document as a digital object. And then within that you have these digital object entities like tables and figures and authors, and they all link to each other, co-authors link to each other, so you have this whole big graph of authors and venues and papers and sub-objects of papers, and this particular section in this particular paper refers to that particular paper, so information at a much granular scale that was being used in a whole bunch of our search algorithms. We did a bunch of work on extracting information from figures. And I will, so I'll not go into the details, but what we were trying to do is we were extracting the x-axis and the y-axis. And sometimes, you would see 4 figures like this packed in one figure. So we would have to first get the sub-figures by looking at, again, white space. And then we were looking at the x-axis and the y-axis, and then we were looking at legends, if you have the legends, reading the numbers along the axis to figure out, okay, is this 10 or is this 1 or whatever it is. And then we look at the points and the lines and extract those points and the lines to reverse engineer the data. In a bunch of cases, this is reasonably easy to do. In a bunch of cases, it's devilishly hard. The lower right bottom is possibly a 3D image, 3D figure which has been mapped into 2D, which is lossy by itself, and there is very little chance of us getting the whole 3D data out. So primarily we focused on 2D figures, looking at points and extracting the points, looking at lines, and where the lines are intersecting, figure out where their continuation is, and so on and so forth. And to some extent that worked. In some cases, the points would, you have a circle and a triangle to denote different things, and a bunch of triangles and a bunch of circles would be clustered in one space, and then we would do our best to recover those using essentially we would extract a bunch of things and using shape detection if they are jumbled. So that's sort of the whole technology of all what we were doing to detect axes and so on and so forth. So I think that's, so these are overlapping points, and we are trying to detect how many triangles there are and how many squares and all sorts of things, and how many diamonds and so on. And of course, we don't really have the gold standard for these. Some of the authors have passed away, so. So there are OCR issues still that needs to be worked on. I think that's where I will stop now. I hope I have given you some introduction to the type of information extraction and search that we have enabled in a whole bunch of different domains, and tried to figure out what to do, how far you can push things automatically. With deep learning, especially at Allen AI, which is an AI institute in the US, they are doing a whole bunch of they are redoing a whole bunch of our work. They have much more bandwidth to do the table extraction and figure extraction using deep learning, and they are getting better results. But that's roughly where I will stop. And yeah, so this was the OrCam that we used. Microsoft supported us. Oh, eventually, this was a 5-year project. Eventually, Dow Chemicals were very interested in this and used it in their, we had to send a student to implement this in their company. And so it was a moderate success. I'll stop there, take questions.
Thank you very much. So yes, we have time to take a couple of questions. Ooh, it was almost a dead heat. We'll maybe start over there first. Thank you. I now have the microphone, I see. More fitness. It's those 2 hours from New Zealand to get here, so I have a bit of time.
Just a very quick question. When we use databases and do the regular searches of Marcus structures and whatnot, we then construct and get all these structures straight from a Marcus search. How is this different from that?
The thing is that in this case, we are trying to extract these things from PDF documents. And I'm not familiar with your databases, but I suspect that that's not being automatically, that's already there in the database.
No.
No?
No. In the pattern databases,
Right.
we actually construct the molecule.
Right. So that's there in digital format.
But we search and we try and look at the molecule that I'm interested in. We actually construct it and find out whether somebody has worked on those or the generic forms. So we actually do that sort of search. So I don't know what the mechanism is. So I, as the user, find it fairly transparent and simple to really do a Marcus search.
By hand.
On a regular basis.
Right.
So I was just trying to find
Yeah, so the point is, well, I'll have to go and look into the database that has, and how you go from your diagram to that. And that's sort of the part that we were trying to automate. But yeah.
And if we take one more question here, then I think we're probably close to time, because I have one more thing to do.
I was curious because chemistry publication has actually evolved tremendously since 2012.
Yeah.
And a lot of material actually has gone into supplementary material, which is not published by the journal at all.
Right.
In fact, most of the tables you find, which would be of interest to chemists, which is something that we might like to mine,
Sure.
would actually be in the supplementary material,
Right.
which I'm not sure is actually collected, is actually covered under copyright, because a lot of them allow you to
Sure. Freely.
download freely the supplementary material, including American Chemical Society, Royal Society, and the others, but they don't do the same thing for anything given inside the paper. And so I do know a lot of people, chemists, fellow chemists like me, who have actually managed to repeat the table in the supplementary material. Because even if you don't have access to something behind a paywall, at least if you download the free stuff, you get what is needed. And these days, and it doesn't look like your project has actually evolved towards that. And why is that? Because I would have thought you would have first applied it to that, and then gotten yourself embroidered into any issues with the copyright, rather than go for the free stuff first. Because there is a lot of it out there, and there is no one to search and catalog them.
Right. So that's an excellent question. So that data that is there, the hope is that modern data will be generated and published where you have the data and the metadata, and none of what we are doing is reverse engineering. And none of this reverse engineering should be necessary in an ideal world. But that's not the world we live in. But we were also playing with this to make a general technology which would work. Let's say we have tried this on financial data to extract from reports. And even there you can publish the data in a database, and then you will not need to extract it. So eventually, if everyone publishes their data with metadata in a nice database table, then none of this work is useful, except still for legacy data.
Right, so thank you for that. Yes, but I was going to comment that this feels like the future should be linked data. We should get our chemists
Absolutely.
publishing their papers and sort of learning about ontologies and linked data, and then
Absolutely.
the future will look a lot brighter. Please, everyone, please stay there because I have one more thing to do. But could you first of all join me in thanking our presenter now? Thank you.